Hi. So in our last lecture, we talked about the Lorentz transformation equations briefly, and we discussed how Lorentz had come up with these equations assuming that the luminiferous ether was true. And so then later, Albert Einstein re-derived the Lorentz transformation equations, but without the need for an ether. And this was published in 1905 for his special theory of relativity. Now, in this famous paper, he derived the Lorentz equations without an ether based on two postulates. One was that the speed of light is the same in all inertial reference frames, and two, that the laws of physics are the same in all inertial reference frames. Now, this is a generalization of the principle of Galilean relativity, which refers only to classical and the laws of mechanics. The presumption here is that the results of any kind of experiment performed in a laboratory at rest have to be the same when performed in a laboratory that's moving at constant speed past the first one. So this is the same fundamental assumption as Galilean relativity. And then we're back to the assumption that we came into before this whole ether thing happened, which was that there's no preferred inertial reference frame, and that it's impossible to detect absolute motion when you're in an inertial reference frame. In other words, it feels still to you. Everything feels normal to you within your own frame, and you don't notice anything different. Now, there's consequences of special relativity. In relativistic mechanics, when you're working these problems, you kind of have to abandon the idea of common sense. So this is your sort of everyday experience of the world. These sorts of assumptions, they kind of go out the window a little bit, and it's a bit of a mind bender, so buckle up, buttercup, I guess is all I can say to you. Here's the fallout from all of this, and we're going to talk about one of these concepts today in this lecture, time dilation. So what we'll see is that there's no such thing as an absolute length, that the length measured depends upon the frame of reference in which you're in. And it really is that length. So I could look at a meter stick in my own frame and it would look like 1 meter long. But if I look at a meter stick moving by in a spaceship traveling at half the speed of light, that length will look different. And it not only will look different, it will be different, okay? And that's the way it is. There's also no such thing as absolute time. We think of time, we deal with time every day in our experiences. Our lives are based on the concept of time, how many heartbeats we've got. A second is a second. We grow up with these assumptions. However, we're going to see that events at different locations that are not observed to occur simultaneously in one frame are observed to occur simultaneously in one frame are not observed to be simultaneous in another frame that's moving uniformly past the first. Okay? Also, you'll notice that if you measure the time that it takes for an event within your own frame of reference, that the time it takes for that same event maybe outside of your frame of reference will be measured as a different time, and we're going to discuss that today. Now, one thing that you can keep coming back to, though, is that observers in two different reference frames will agree on the speed of light. They'll agree that c is 3 times 10 to the 8th meters per second. They'll agree on that. And they'll also agree on their relative speed. So what I mean by that is that let's say that I'm in a spaceship and it's traveling at half the speed of light, okay? And then my spaceship travels past someone in a stationary frame on the ground looking up at my ship, okay? From the person on the ground, they will say, she is going past me at half the speed of light. And I will say, hey, I'm still, but that person on the ground, that person is going that way at half the speed of light. So we may not agree on who's moving, right? But we will agree on what the relative speed of that movement is, if that makes sense. Okay, now, let's use these ideas to help understand the concept of time dilation. Now, if this is a new vocabulary word for you, dilation, just remember that when you're at the eye doctor and they dilate your eyes, your pupil gets larger. So time dilation is time seeming longer or time being longer for an event, okay? Now, what we're going to use for this is sort of the thought experiment of two observers. And one of the observers is in a moving train, and the other observer is on the ground watching as the train goes by. Those two observers are going to figure out what the time is, the time interval for an event happening on the train. Okay? So for the sake of argument, let's assume that the person on the train is determining how long it takes a light pulse to be emitted from, say, a laser pointer or something, and then travel up to the top of the train, reflect off a mirror, and then come back. So they're measuring the amount of time that it takes that light pulse to go from the bottom of the train car to the top of the train car and back again, okay? So we'll call the emission of the light pulse from the laser event 1, and the detection of that light pulse at the detector right next to it event 2. And then the interval between those two events we'll call delta t, okay? So there's the observer that's in the moving train. We'll call the observer, this observer O prime, okay? For the moving, remember the moving frame, we'll call the prime reference frame. We're also going to assume that this train is moving at a relative speed u with respect to the observer on the ground, okay? And we're going to assume it's moving to the right. So this observer in O prime carries a clock or some sort of detector that can measure the time interval between these two events, event 1 and event 2. Now, the observer on the train will call her time interval that she measures delta t naught there, okay? So the amount of time that it takes the observer on the train to measure this would be equal to 2d over c. Remember that a speed is equal to a distance divided by time, and so rearranging, we have a time is equal to a distance over a speed. So since the light is traveling at the speed of light, both observers agree that c is c, okay? The observer on the train sees a distance of 2d. In other words, the height of the train car is d, and it goes up and then back again, so 2d is the total distance divided by c. And that's the time measured by the observer O prime, okay, delta t naught, 2d over c. Now let's talk about the second observer. There's a guy here on the ground, and he's watching this event take place. We'll call him observer O. Remember, we use the unprimed frame for the stationary frame. So that's a stationary observer on Earth. He agrees that the train is moving at a speed u. So the woman on the train would say, oh, I'm going past that guy, he's moving behind me at some speed u. And the guy on the ground would say, oh, she's moving to the right at speed u. So in other words, they disagree on who's moving, but they do agree on their relative speed, which is u. They also agree on the speed of light, c. Okay? So, according to observer O, he observes the mirror and O prime moving with that speed, and he sees that by the time the light from the flashlight reaches the mirror and then comes back again, that train has actually moved to the right. So, according to him, all right, the light doesn't go in a straight line up and back. It instead makes a triangle, okay? It makes a triangle as shown here in orange on this little graphic, okay? So, it's not going straight up and down according to him, it's making the top of this triangle. Now, since both observers have to measure the speed of light to be c, and both observers agree on their relative speed, which is u, then you can see that in order to make that work, the light, which is traveling farther for the stationary observer, has to take a longer time, right, in order for the speed to be the same. Does that make sense? So your time interval that we're going to measure for the stationary observer, I'm going to call that just delta t. Remember, delta t naught is the time observed for the person on the train, and delta t is going to be the time observed for the person that's stationary. So if you look here, you can just do a little simple, easy trigonometry, okay, a little geometry here, and figure out what the relationship for that time interval is, okay? If the train is traveling to the right with the speed of u, then in the time that the light pulse travels, then the distance that that train travels is going to be u times delta t, where delta t is the amount of time measured for the event for the observer on the ground, okay? Now, you can see that these two legs, D is going to be the leg of the triangle for the vertical direction, which is the height of that train car, and then you're going to have the bottom of the triangle, right? And then you're going to have the distance the light pulse traveling being the top of the triangle. So using just the Pythagorean theorem, we can solve for what this time interval is going to be. Delta T naught for the person on the train is just 2d over c, but the time interval measured for the person on the ground would instead be this distance for the top of the triangle, and we would plug that in and then divided by c. And so here we get 2 times the square root of d squared plus u delta t over 2 squared, right, divided by c being our time interval. And you can see that the time interval for the person on the ground is going to be bigger, right, than the time interval for the person in the train. That's time dilation, okay? So I've got this kind of cool looking expression right here that I got out of my Pythagorean theorem. Let me show you here. If I do a little bit of algebraic manipulation on that expression, delta t is equal to 2 times the square root of d squared plus u delta t over 2 squared divided by c. That's what we had on the previous slide. If I square both sides of that equation, I get delta t squared is equal to 4d squared over c squared plus u squared over c squared times delta t squared. If you don't follow that, pause the video and make sure that you can follow that algebra to get from step 1 to step 2. Then I bring everything with delta t squared over to the left-hand side of the equation, and I end up with delta t squared is equal to 1 minus u squared over c squared, and that's equal to 4d squared over c squared. Now, I want my expression to just include the straight-up times. I don't want the times squared, so I'm going to take the square root again, and I end up with delta t times the square root of 1 minus u squared over c squared is equal to 2d over c. Now, if you remember, our equation for the time interval measured by the person on the train is delta t naught is equal to 2d over c. So you can see then that I can just plug in delta t naught for this 2d over c here, and then I can divide both sides by the square root of 1 minus u squared over c squared, and I end up with this expression. Delta t, which is the time interval measured for the person on the ground, is equal to gamma times delta t naught, where delta t naught is the time measured by the person on the train. Now I'm going to use this gamma factor over and over again in special relativity, okay, which is why I gave it a special name. And gamma I'm going to call 1 over the square root of 1 minus u squared over c squared, where c is again the speed of light and u is the relative speed of the two frames. All right? So this is the expression for time dilation. Okay? What this means is that the person on the train measures a certain time, delta t naught, and then that time is dilated or lengthened, made larger, by a factor of gamma if you observe that event outside of the reference frame. All right? Hopefully that's clear. Now, I derived that for this special little case. Okay? So to sum up, the time interval delta t between two events measured by an observer moving with respect to a clock is longer than the time interval delta t naught between the same two events measured by an observer at rest with respect to the clock. The way that we say that mathematically is delta t is equal to gamma delta t naught. Okay? Delta t naught is often called the proper time or the time measured within the reference frame of the event. Okay, so that's the thing to remember. What's the proper time? The proper time is the thing measured with respect to the reference frame of the event. If you're observing an event outside of the reference frame in which it occurs, then the time for that will be dilated. Okay, so this is time dilation. Now, the little derivation I showed you with the triangle on the previous page, this is a nice derivation for this particular occurrence. It's not a formal derivation of time dilation, but I hope it does help you to conceptualize time dilation and help you wrap your head around it. Now, I have a little cartoon for time dilation. So here's the two people on the train. Okay, I'm going to reset it. Now you can see that we've got their origins coinciding at time t is equal to 0, and I've got the speed of the train as a fraction of the speed of light that I can dial in. So we're going to assume that the train is traveling at half the speed of light with respect to the observer. And then I can press start and you can watch what happens here. So you can see that the event takes longer for the observer outside of the frame. The time is dilated. If I dial up the speed of light even more, say to 0.9 c, reset and start, then you can see that it takes a lot longer for the observer that's outside with respect to the observer that's inside. So the time is dilated by quite a bit. Okay? Okay. Let's talk a little bit about this gamma factor because it comes up again and again and again. Now, one thing to understand is that you've got that gamma is equal to 1 over the square root of 1 minus u squared over c squared. So for most everyday speeds, we're not traveling, we're not seeing events most of the time that are occurring at a significant fraction of the speed of light. If u goes to 0, then gamma goes to 1 because it's 1 over the square root of 1 minus, right? And so the minus part just pretty much goes to 0, which means we have 1 over 1, and it's 1. Okay, so you can see here that if you plot what gamma is as relative to the speed of light, here we have on the horizontal axis the speed of the frame, and it goes from 0 to 3 times 10 to the 8th meters per second. And then we plot gamma on the y-axis. You can see that it's 1 for a really long time, and then it deviates kind of slightly, and then as you get closer and closer to the speed of light, it blows up. Okay, so time dilation is not observed in our everyday lives, and it didn't get really documented and observed until, you know, much later in our history, just simply because most of the things that we interact with don't go anywhere close to the speed of light, and so gamma is pretty much 1. Okay. Here's a table showing some of the values. If you're at 0.1% of the speed of light, you'd have to work really, really hard to see any deviation from gamma. We've got 1.00000005. Okay, so you have to work pretty hard to see that gamma's not 1 at what I would call everyday speeds. Now, one thing that students have the most trouble with when they're doing these time dilation problems is identifying which is the proper time. So to remind you, that time interval, which we'll call delta t naught, that's called the proper time interval. The proper time interval is the time interval between the events as measured by an observer who sees the events occur at the same point in space, okay, or within its own frame. Okay, so for example, if an event occurs in the moving frame S prime, then to the observers in S prime, they occur at the same place. To an observer in a stationary frame, the event's moving in space as well as time, and so that's the outside observer, so that's not the proper time, okay? So to get back to the train, the woman on the train saw the light pulse move from her hand basically to the detector right next to it, okay, up and back, and that is basically the same point in space. So within that frame, that's the proper time, okay? Now, these problems are really not that tricky mathematically, algebraically, they're not that bad. It's just, you know, delta t is equal to gamma delta t naught. And solving for gamma is really not that difficult. However, sometimes identifying what's the proper time interval is kind of difficult, and that's where the real skill to solving these problems is. So to generalize, if a clock is moving with respect to you, then the time interval between the ticks of that moving clock is observed to be longer than the time interval between the ticks of an identical clock in your own reference frame. All physical processes are measured to slow down when these processes occur in a frame moving with respect to the observer. This is real, okay? This is not just some sort of geometrical trick, okay? This is real. The processes can be chemical and biological as well as physical. In other words, aging would be different, okay, for someone moving on a fast train as opposed to someone standing next to it, because your heartbeat and all the other chemical and biological processes taking place in your body is basically the same as the ticking of a clock. This has been verified experimentally, okay, so it's real. There's been a couple of ways it's been measured. We'll go over them now. The atomic clock measurement is one, and this is an experiment that was done where 2 planes took off at different times from Washington, D.C., where the U.S. Naval Observatory is located, and the planes traveled east and west around the Earth as it rotated, and atomic clocks on the airplanes were compared with similar clocks kept at the observatory to show that the moving clocks in the airplanes actually ran slower. So they verified this experimentally. Another verification is a muon, okay, and the time that a muon decays. What's a muon? Well, muons are unstable particles, and they're created in the upper atmosphere when cosmic rays collide with it. And they have the same charge as an electron, but a mass that's 207 times more than the mass of an electron. Most muons that are observed on Earth, as I said, are produced by primary cosmic rays that interfere and collide with atoms in the upper atmosphere. So they're roughly half of the cosmic radiation that reaches Earth, and we get a fair amount of cosmic radiation here on the surface of Earth. It's very measurable. Muons have a half-life of 2.2 microseconds when measured in a reference frame that's at rest with respect to them. This has been done experimentally in laboratories. They've measured the lifetime of muons. Relative to an observer on Earth, then the muons should have a lifetime of gamma delta T naught. So what happens is they keep seeing these muons at the surface of the Earth. But given that the speed of the muons was pretty much known, and given their half-life, they never should have made it to the surface of the Earth. They would have only made it 6.6 times 10 to the 2 meters from where they were created, given their speeds and their lifetimes. However, we do see them very regularly on the surface of the Earth as they're measured, and that's a much further distance, right, from where they're created in the upper atmosphere to the Earth, okay? 4.8 times 10 to the 3 meters or so. So there should be no reason that we would see a bunch of muons at the surface of the Earth. But because of their speed, you see, they're traveling at a significant enough fraction of the speed of light that to an observer on Earth, where the detector is, okay, time is dilated. So the muon sees a different time than we do, and therefore, since it sees a different time than we do, it's within its own lifetime. To us, it would seem longer, and they make it, okay? This has also been measured at CERN. It measured the lifetimes of the muons in agreement with the predictions of relativity. So all this is real. It's a little hard to wrap your head around, but time dilation is a real physical effect, and we can measure them, okay? Let me show you a pretty quick example on how time dilation will work in a problem. Okay, so here's the problem. An observer on a spacecraft with a velocity of 0.7 c, that's 70% of the speed of light, relative to Earth, finds a car takes 40 minutes to make the trip. So in other words, they're watching this car drive along on the surface of the Earth, and they're timing how long it takes from when the car stops to when it starts to where it reaches its destination and stops. And they measure that time as 40 minutes. So how long does the trip take to the driver of the car? Okay, well, the first thing that you have to realize is what goes where, which one's the proper time, and which one's the dilated time, okay? So to understand that, you have to think about where the clock is. So you see here, it says an observer on a spacecraft finds the car takes 40 minutes to make a trip, okay? But the car isn't on the spacecraft, okay? The car is on the surface of the Earth, which is the stationary reference frame. So that means that the proper time would be the time as measured by the driver of the car, not by the person on the spaceship. Okay, so that's how we know what's the proper time here. Okay, so this would mean that delta t would be the 40 minutes. It's measured outside, it's the dilated time, and delta t naught, which is the time to the driver of the car, the proper time, that's what we're solving for. So now all that's left is to figure out what gamma is. Well, gamma is the square 1 over the square root of 1 minus u squared over c squared. So if we plug that in, we plug in 0.7 c for the speed, and then c squared, of course, for the speed of light, and we solve for gamma, and we get 1.4. So now we have delta t is equal to gamma delta t naught. Remember, delta t is the 40 minutes, because it's measured outside of the frame, and that's equal to 1.4 times delta t naught, which is what we're solving for. So we're going to divide 40 by 1.4 and solve for delta t naught, and we get 28.6 minutes. Okay. Another thing that hangs students up sometimes is the realization that gamma is actually a dimensionless number, and so you can plug whatever you want to in terms of the time as long as the units are consistent. So you see, I didn't have to shift out and switch to seconds or anything to the SI unit. I can leave it in minutes because I have a dimensionless factor there, gamma, in the equation, and so as long as I understand that it's minutes on the left and minutes on the right, I'm good to go. Okay, well, I hope that's clear, and I'll see you in class.